then I can say for sure that all its neighbors must be compromised. Right? Because S is not compromised and I have an edge between S and its neighbor, then the other one must be compromised. Remember that in each edge, one of them must be compromised. Okay? So I know that at least here, all the neighbors are compromised. I remove S and its neighbors and let the resulting graph be GS. Then how many compromised nodes in the resulting graph? At least you have the number of minimum vertex covering of GS to cover the remaining graph. Okay? So if I assume S is not compromised, I know that there should be at least NS plus the minimum vertex covering of GS number of nodes are compromised. Right? So if this number is bigger than K, then I found a contradiction because K is the upper bound of number of compromised nodes. So if this is bigger than K, that means that my original assumption is not correct. So node S must be compromised in this case. Okay? And we show that this is not only a sufficient condition to say that node S is compromised. Actually, this is also a necessary condition. So if you can identify all such node S, then you can actually get the complete compromised core you want to compute, and without introducing any false positives. Okay. So in general, our algorithm is composed of the following steps. For every node S, I'm just going to get rid of S itself and all its neighbors in S. Then I'm going to compute the V, which is the size of the minimum vertex covering of the remaining graph, GS. Okay? If V plus the number of neighbors of S larger than K, then I know that S is compromised. Okay? But as you all know, that minimum vertex covering is NP complete problem, so you don't want to compute it. So in our algorithm, we're actually using some lower bound to approximate the minimum vertex covering. What we use is a maximum matching as a lower bound approximation.
Can you do one slide? The if statement at the end, you are computing some metric and comparing it to K. Mm-hmm. Isn't it very analogous to reputation-based techniques?
I'm sorry?
Isn't it very similar to reputation-based techniques?
Very similar to reputation-based
yes.
techniques.
Where the reputation here is someone telling on you that you are misbehaving or no. Mm-hmm. So it is very related to reputation-based. Right?
Well, yeah. Here we're using the topology information to get a closer bound of the number of compromised nodes because I know that NS is my neighbor. Okay? But in a P2P system, for example, you cannot make. We don't know that. Right? You don't know which because anybody can be your neighbor in the P2P system. And also, because in sensor network, several nodes can observe the behavior of the same node. Okay? But in P2P, usually, one transaction, there's only two parties involved. Okay, so that's the difference between the typical P2P system and sensor network system. In fact, in later experiments, we're going to compare our approach with a well-known P2P reputation-based trust function to see what's the difference between them in terms of performance. Okay. Okay, so instead of really compute the minimum vertex covering of a graph, we actually use the maximum matching as a lower bound approximation. Okay. Note that here we don't want upper bound approximation. We only want a lower bound approximation so that we're not going to introduce any false positive. Okay. But maybe we're not going to identify all the nodes in the compromised core. But I'm pretty sure that I cannot introduce false decisions here. So now come to the question previously asked. Suppose after I remove all those compromised nodes, there may still be suspicious pair remained in my graph, right? I mean, so what happens? What should we do with those nodes? Okay, with those nodes, we cannot make a reason for sure that which node is compromised. But again, because this is a sensor network, I want to achieve optimal security of the network. I may just sacrifice some nodes Okay? I may have a trade-off between the detection rate and the false positive. So one easy way is that I just identify the maximum matching of the resulting remaining graph all as compromised. Okay? And so given one pair, I know one of them must be compromised. So if I identify both of them as a compromised, I introduce at most 50% false positive rate. Okay, that's a bound I can guarantee. Okay, actually I can do better. Suppose I don't identify maximum matching, identify all those triangles, disjoint triangles in the remaining graph. Then I can lower down the false positive rate to 1/3. Okay. So in summary, our approach is composed of two phases. In the first phase, I'm going to approximate the compromised core. In this phase, I'm not going to introduce any false positives. Okay. Then in the second phase, I'm going to use maximum matching to further eliminate compromised core in the resulting remaining graph. Okay. Okay. To verify our approach, we set up some simulation here. So in the simulation, assume that sensor nodes are randomly deployed in a 100 meter times 100 meter area, and they are sensing the temperature and report the temperature back to the base station. And we also assume that there are 10 to 15% nodes are compromised. Okay, and we actually assume a strong collusion model. That means those sensors always collude with each other. They're totally coordinated. So I don't issue alerts against my another compromised node, and if we observe the same node, we're going to issue consistent alerts. Okay. In other words, there's no edges between compromised nodes. Okay. But we don't assume the base station knows that. The base station may still just assume the compromised nodes may behave whatever way they want. Okay. So it cannot take advantage of this information. Okay. So what do we care here? We care about two things. First, detection rate. That means how many compromised nodes I can identify. Okay. Another one is false positive rate. That means how many wrong decisions I made after I identify compromised nodes. There are several parameters we want to determine their impact on the performance. So the first one is deployment density. Intuitively, if you only have several beacon nodes, several nodes in your network, you cannot do much. Okay? But if you have more nodes in the system, then the behavior of one node may be observed by a lot of other nodes. Okay? So in that case, we may choose better. We want to observe what is the impact of deployment density to our algorithm. Okay? And the other one is accuracy of security estimation. Maybe you just make a wrong decision, which you are very conservative. You assume that there's so many nodes may be compromised, but actually there's only a very small number of nodes actually compromised. Okay, so we're going to see that what is the impact of accuracy of your security estimation on our algorithm's performance. Okay, so we compare the following algorithms. The first one is called general only. That means this algorithm is only composed of the first phase. I compute the compromised core, I stop there. Okay? So in this case, I'm not going to introduce any false positive, but I may miss a lot of compromised nodes. Okay? And in the second is called general plus MM. That means I have a two-phase algorithm. I compute the compromised core, then I'm going to use maximum matching to further eliminate compromised nodes. Okay? I may identify more, but I may also introduce false positives. And we also have implemented another algorithm called eigenrep. This is a well-known reputation-based transfer function for P2P systems. So this algorithm is very similar to a page ranking algorithm when you try to fetch a web page by a search engine. Okay? So by running this algorithm, when the algorithm stops, it's going to give a trust value for every node in the system. What we do is that we just